Today now that we're recording. We will be covering C++ today. James is going to take you through setting up a basic project. Not quite sure if he's going to cover loading libraries or if everything is going to be completed ahead of time, but I'm sure there will be some benefit to this to everybody. We will then do some basic drive. We'll do some basic movement. We'll drive with PID for your encoders and so on, and get different actions done and so on. So if you haven't got a robot complete and a robot wired up to drive the robot, you can still go through the code and build everything, and use it as a basis for when you get going. And any questions in the future, of course, on what we've covered, you can always send us a note and we'll try to help you as best we can to make you successful. All right. So with that, I will turn that over to James. And which camera are we on? Can they actually see us?
Yeah.
Okay. Or can we just see the robot?
That's what they see right now.
All right. Okay. So James, let's get started and away we go.
Yeah. So we'll start by, I just opened up Visual Studio Code so that we can start from scratch for creating a program here. Yeah. So when you first open it up, you might have a previous project or a blank screen like this. And as you can see, there's no command palettes or anything. So you can do the Control-Shift-P or Command-Shift-P on Mac. But there's also a shortcut that if you hit F1, the command palette will open up. And I want to look for create a new project. So WPI lib create a new project. If it's not there, you could type it in. Create a new project. Well, and this is the project creator. So we're going to create a template. And then we want CPP, so C++. And our base project is going to be a command robot. Then select the folder to place the new project into. Let's just call this training. A project name, let's call it X drive. And then the team number should match your wireless SSID from your VMX. So by default, that's WorldSkills-1234. So I'm going to type in 1234. This is to ensure that when you compile your project and when you send your project over to the VMX, that it uses the correct IP address when sending it. Then I'm going to hit generate project. I'll do it in the current window. Now, when it first creates the project, it's going to run a build so it can cache and build all the default libraries inside the project. Sometimes this can take a while depending on how your internet connection or if the Gradle server is running it on your computer. So as you can see right here, what it's doing is it's trying to search for certain files, which is not inside the project yet. So it's just grabbing them from the internet and then compiling.
Now, once you start your project, does it need to download all these files every time? Or when you do it for the first time, are they there and you can save the project and not require the internet connection?
So internet connection is only required on first building of the project, or if you add a vendor library. Otherwise, you can go completely offline. Which means if you have your code ready to go at a competition, you don't need the internet. So now that I have a successful build, I'm just going to close here. And as you can see, we do not have our NavX or Titan vendor library yet. So that's the first thing I'm going to add to the project. So I'll do this, the Studica one first. I have the links on another screen, so I don't have to go look for them, but you can find them on our docs page very easily in the programming section.
He wants to know the advantage of using either Java or C++.
Well, C++ allows you to do almost real time because that's just the way C++ is. Or Java is a garbage collector language, which means it runs higher level than the C++. So Java is much easier to program, but C++ will give you a small advantage. The amount is not the greatest, so it's up to you really if you wanted to do it or not. So to add in a vendor library, I'm going to open up the command palette again, and I'm going to look for manage vendor libraries. So you can see it here. You can also type it in and search for it. And then I want to install a new library online. So I click that, and then it will ask for a vendor URL. I'm going to paste mine in and then hit enter. A prompt will come up saying it is recommended to run a build. And the reason for this is right now, all you did is you just added a JSON to your file where you haven't actually grabbed the library yet from the internet to cache into your computer. So if I hit yes, the build will run a build and see that the library is not cached, and it will download it and then cache it into your system. So I'm gonna hit yes.
Right. So that's important when you load the vendor libraries to do the build. That way they're cached locally on your system for this project. And when working in this project, you'll not need to be connected to the internet again.
So I've added the Studica JSON. So this creates the vendor library for most of our products. The only thing we have to add now is the NavX JSON. So that's if you wanted to use the internal NavX on the VMX. So I'll just copy that link, which you can also grab from our docs page. Just want to get rid of it. Always in the way. So manage vendor libraries again. Install new libraries online. Paste the link. Hit enter. The prompt comes up again. I hit yes. And as you can see, build successful. So everything's good to go so far. Now there's one last thing we need to do before we can switch over to programming the VMX. And that's if you go to the build.gradle, you can see that it's still targeting the RoboRio, which is the base default for the WPI libraries and programming system. So I just want to convert this that it will target the VMX instead. So if I go up to the VMX.py command palette, I can then say change deploy target to VMX.py from RoboRio. I'm going to hit that. And what that will do is it will change your build.gradle to then target the VMX.py. It'll also download the latest HAL and updates for the VMX.py at the same time, because it actually you can update your VMX from when you send a build over to it because it's bundled in. Now I have a build successful. And theoretically at this point, I no longer need to connect to the internet at all. I can go offline because I've grabbed everything that I need from the internet. So to go over the program structure here, all our code will be inside the source folder, the main, and then a test folder. Test, there's nothing really there. That's more for advanced usage, so we can ignore that. In your main folder, you have your source code, your header files, and then a deploy folder. The deploy folder is just the folder that if you wanted to send over certain files to the VMX, you could put it in there. And when you send it over, when you run deploy, it will send those files over to that location. So if you have vision pipelines or other code that needs to run, it can go in there. In my include folder, all the headers are there. And in the CPP, the source, I have all the source of the headers. So always to start with a project, I want to work on the constants class, or the constants header. Because what this header file is it maps out your robot in the code form. So I can take how I wired the robot here. So if I ever change the wiring on the robot, I just need to change the value here and not have to go change it on every single place of the code that I use it. So to start, I'm going to create a namespace. I'm just going to name it constant. You can name it whatever you want, but I like to try and keep it easy. And then because we're going to be using some predefined values here, I might type in that. There. You map the files. Now I add this because we need to get the pi constant for one of our calculations with the encoders. So we have to include those two lines to get that proper constant in. First thing I like to do is map out the motors. So I'll add a little comment here to say motors, and then we'll start creating the constants for those motors. So static constant expression. I start with the Titan ID. So each Titan has a unique CAN ID that you can create. By default, it's 42, and you have a range of between 1 and 63. So theoretically, you could have up to 63 Titans on a robot. Would it work properly? Probably not. But yeah. And then now I can map out each motor on our robot. If you remember, our robot's using 4 motors because we're doing an X drive. So I'll call the front left motor front left because that seems pretty obvious as to what it is. And the motor port for that is M2. So I'm going to put 2.
So if you remember when we built the robot yesterday and we mounted the motors, I talked about getting a little sticker and labeling your motors. So setting the direction that is going to be front for the robot, and then deciding which motor is which on which port. So 0, 1, 2, 3. Okay. So now you're just defining that port number for each motor. So the front left is on motor port number 2. Okay. And so on. And the thing about what James is doing here is by setting this in the constants.h, if you have to change a motor port for any reason, you don't have to change it in the rest of the code. You just have to go in here and change that number, okay? And it will update everything else.
All right. Now,
yep. We got a fly in here. It's bothering us.
Now that we have the motors, I'm going to add some sensors that we plugged in. So some of those sensors are the encoders. So I'll put encoder. Now the encoder, we don't actually need to know the port because we are plugging them into the Titan. So we can use the motor port values as the constant for that when we need to map it out. But what we do need to do is calculate the distance per tick that the wheel will be doing in relation to the motor encoder. So there are some values and math that we need to do to get that final value. So the first value is your wheel radius. So because we're using the Omni wheels, they are 100 millimeter Omni wheels. However, if you were to actually look at the Omni wheel, because of the way they are, it's actually about 102 millimeters if you measure it correctly. So I'm going to put 51 there as my radius, as this will give me a little bit more accurate of a count. Oops, these should be doubles, not ins. So now my pulse per revolution, if I was to just turn the motor shaft once, I would get an exact count of 1464. So this is my pulses per revolution of the motor encoder. Now I add a gear ratio in here. And the reason for that is sometimes you're not mounting your wheel directly on the motor shaft. You might have a gear ratio in between. For example, if you're doing an elevator or something like that, you want to just change the ratio value here, and you won't have to calculate for that in your code. It's just a simple change here, and it's changed your distance per tick to accurately measure that correct. I can't fly somewhere else.
I don't know. It's irritating.
So you can see here how we incorporate the gear ratio with the pulse per revolutions. As if we had a 2-to-1 ratio, we'd actually, this value would have to be double than what it currently is, so that we get a correct calculation. As, for example, our wheel would have to spin once, but our motor is actually spun twice, so the count is double. Or the opposite way of the count will lower if your motor spins only half, but your wheel is spun once.
Pissed.
So what we've done here is to calculate our distance per tick. We take the circumference of the wheel and then we divide it by our encoder pulse ratio. And this will give you a distance per tick. So as the wheel spins, you know the exact distance that you travel. So you could take this distance per tick and then times it by the encoder count that you have. And this is done for you in the background already, so you don't have to worry about it. But we do need to know this value to get a correct output for you. Then we also have some inputs and outputs on our robot. So I'm going to map those out too. So I mapped out the start and stop button, and they are in the digital input ports 9 and 11. So I just put 9 and 11 right there. We do have some outputs. And that's the two LEDs on the control panel that we also wired up and mounted. And they're in ports 20 and 21. So I put 20 and 21. And that's it for the constants class. And we just go ahead and save it and it's good to go. So now that we have our constants class, we can actually start going and creating our subsystem code to where we can map everything out that we need. So in subsystems, there's already something there. I'm just going to leave it for now and we will add something in later. A new file. I'm going to type in training.h, hit enter, and it will open the file for you. We need to do a couple includes so that we make sure that we have all the header files that we need for our code. So I'll just quickly type them in and then I'll explain them all for you.
Now, these are generally the same for each project, correct? So you could, have a default project set up somewhere, and as you're creating new ones, you could just cut and paste as long as you're not changing anything. So it's important as you're developing to, think about where your wiring is, think about what standard inputs are, and I would document those so that you can just reuse code each time, so you don't have to continually type all this in.
That's so annoying.
You've got 9 you're going to put in here, I believe.
A lot.
Yeah.
All right. That was a lot. So to go through the imports, we have our subsystem base. This creates the subsystem that we want. As the way this works is you have a subsystem and then you have commands. And the commands use the subsystems to drive your robot around or operate different tasks. And your subsystem, you could break out into multiple different files. For example, a drive base would be one subsystem, an elevator would be another subsystem, your claw could be another subsystem, and your vision would be another subsystem. And the reason for this is it branches out the code so that if you know if something's not working correctly, it must be related to that subsystem. Oh, it's driving me crazy.
I can't until we take a break.
So as you can tell, the header, there's not really much here. So we actually need to create the class that this will go into. So class training. And we actually need to extend it from a different class.
You're just sharing the screen, right?
Yeah. So this is the base right here. So we have our class and we are extending or inheriting the subsystem base, and that's why we need to import the subsystem base. Now, if you remember, C++ classes have a private and a public section. In the public, we're going to put all our constructors and functions and things that you want outside classes to access. And then in private, we're going to put all our localized code that we don't want those other classes to be able to access. So we'll add our constructor first. Then we'll add in some other functions. So for I'll just add them in quickly and then explain each one. So we have the front left encoder, the back left encoder, and then the two right encoders. And then we'll do a little calculation in this get average encoder Y that will give us our average encoder distance as we drive forward. This way we're meshing all the encoders together to get a proper distance that the robot has traveled. Then we have some of the NavX sensors, so get yaw, get angle. I'll explain those later. And then we also have some other functions to reset some values or set some values. So we can reset our yaw, reset our encoder values. Then because we have an X drive, we want to drive it in a holonomic way. So I defined a function called holonomic drive with its input being X, Y, Z. So your X, Y, or Z, depending on what you want to do. And then you have two functions, which is the running LED and stopped LED. And we're going to use this to have the LED on the control panel show when the robot is enabled or when the robot is disabled. Now in the private section, we're going to actually create the instances for all our stuff on our subsystem. So it's fairly simple. We are statically creating the object. So this is the recommended way to do it in C++. And here we're basically creating the object, and then we're assigning the correct constructor values to that object. And now whenever we use this object inside of our class, it's already created and we can use it anywhere. I'm going to create the rest of the objects. So if we look at the rest of the objects here, we have the motors. Check this out because we're just going to use the default frequency. Then I also created the encoders. So with the encoders, we say we have to pass the actual motor into it. So that's why your motor should be defined before the encoder, as you need to actually pass the motor object into the encoder, along with the encoder that you want to access. And then you have to also set your distance per tick. And the way this breaks out is that if you have a motor that is using a different encoder or a different gear ratio, you can create a different distance per tick for that motor, and it would correctly calculate the distance. Then we have the NavX that we created here. We're just going to use the internal SPI port to communicate with it, as that's the recommended way. And then I also created the start stop button and then the running and stopped LED. Now we also want to create some variables that we want to store privately that we don't want to be accessed by the outside of our class. And that's regarding our holonomic. No. Variables. So we have our front left. Back left. And you'll see later when we get to the holonomic function about why we created these.
What does that number 0 define?
Oh, we're just assigning a default value to it. You could do this inside your constructor, but you could also just do it straight away in the header when you define the variable. Now we could save our training header and we can actually move to creating the training class source code itself. So to do that, remember we had to create this file. So in the actual source CPP subsystems, there is no training.cpp. So we right click on the subsystem, new file, training.cpp. Make sure to put .cpp as you have to type it in, otherwise it won't work. And we have our blank project. You can always go back to your header file to review what you created to make sure that it's correct. So the first thing, of course, you always have to do is include your header file. Otherwise, your code won't work that well. I'll add this in here and then I'll show you why we have it in there in a bit. So I'll first create the constructor. So the constructor is unique as when you first create the object for your training subsystem, this is what will be called. So sometimes it's a good idea to set some flags or other things in here. So right now I don't have anything to put in here because I haven't created the objects that will use these flags yet. So I'll leave it blank for now. We'll come back to it. And then we'll have our periodic class. Now this periodic class is unique as it's built into the subsystem. What will happen is every time the robot has a loop, so it starts at the beginning again in its sequence, it will call this periodic loop. So this is a great place to put sensor data to send to the smart dashboard or shuffleboard for you to read your data sensors all the time when it's running, to monitor how your robot's running if you want. But we have not created the functions yet to call for that. So we'll leave this blank and we'll move on and then come back to it. So some of the things we want to do right away is reset the encoders. So I'll add some code here to do that. Oops. So here now we have our reset encoders function. So what I'll do is when we call reset encoders, it will reset all the encoder values to 0. I also want to have a function that will reset the yaw. So when we call reset yaw, it will zero our yaw value to 0. So, which is useful if your robot's driving around and you know locations where you want to reset your encoders and reset your yaw to then restart a path or movement. This is a perfect way to do it. Now that we have these two functions, we can go back to our main constructor and we can start the code for that. So I want to reset my encoders and reset my yaw when this is first run. So when the object is created. We then have some motor flags that we want to set. And the reason for this is there's 3 different motor flags. So it could be that your motors are driving in the wrong direction because you always want to assume that a positive value is forward and a negative value is backwards. So motor flags. So I'll put the 3 flags here and then we'll talk about what each one does. So there's 3 flags here for each motor essentially. So the set inverted will change the direction that the motor spins. As if you were to have the robot, if you were to look at the motors, on each side of the your drive, the motor will be actually facing the other direction. So on the right side, we might need to invert them if we want to drive forward, or on the left side, we might need to invert them when we drive forward. And then invert RPM is sometimes when you're getting the RPM that the motor's spinning at, it could be negative. So what you'd want to do is invert the RPM so that it is positive when you are driving forward. Then there's the encoder, as sometimes it may be counting in the wrong direction. As you always want to remember, assume that positive is in your positive direction. And that's the 3 flags for each motor. So what I'm going to do is add the rest of the flags for the other 3 motors, and then we will comment out the ones that we actually need to comment out. So I've added the rest of the flags here, and I've also commented out the ones that we aren't using. So this is based on data from we've tested on the actual robot. So I needed to invert my left motors RPMs to get the correct forward movement. And on the right side, I had to invert the direction that the motors spin, along with inverting the encoder direction itself. The RPM I didn't need to invert, look. And that's the constructor done, and we can move on to other functions. Now we can, let's create the actual holonomic drive here. So remember, our holonomic has some inputs, so double X, double Y, double Z. So here's where we will have some values. Denominator is equal to F9. So let's explain this denominator code a little bit. So what we're doing is we're adding all 3 of our inputs as an absolute value. And then we're using a max function to say that at max this can be 1.0. As with our motors, they have a max range of -1 to 1. So you don't want to go past that. So the reason we do that is to make sure that everything is within that range and we won't have any overrun of value going past that range. Front left. I'm just going to put in the formula here and then we will talk about what's going on. So with the formula here, each wheel is being set based on the values of the X, Y, Z, and then divided by the denominator to keep it within range. So we have our Y values. So that's our forward and backwards. Then we have our X values, which sets our translation, so our side to side strafing. And then we have our Z, which will set your rotational distance that you want to rotate at. Now this is, we're not really gonna go over the math today, but this is the general formula for it. Let's add some more functions. So, oops. So here's just a simple function that will turn the running LED on or off depending on what we're doing. So if we set this bool to false, then it will turn the LED off. If we set it to true, it will turn the LED on. Now we can do the exact same thing for the stopped LED. Now let's create the encoder functions. So what we're going to do is each encoder function will just grab the encoder distance from their appropriate encoder. And then we're going to go into the get average encoder Y, which is where we're going to use for our PID later. What it does is it grabs the encoder of each side, adds it up. So the left encoder and the back left encoder will add them up and divide by 2 to average the left side out. And then we'll do the exact same for the right side, average that out. And then we'll add both of them together and then average that out again. And by doing this, we have a pretty good mesh of our Y translation distance for our robot. And then the last few variables that we'll do here is getting the yaw. And getting the angle. I'll explain the difference of these two when we get to creating the commands. Oops. So now that we have all our functions, we can go back to our periodic where we want to add some code. Now in this code, if we remember, the periodic loop will run every loop. So it's a good way to send sensor data to your computer so you can see what those sensors are actually outputting. Now, I only want this to work when I am debugging my code or I'm measuring data. When I'm actually having the robot run on the core, I don't want this being sent all the time because that's taking up network data and it's extra overhead that's not needed. So if you remember, we created that debug define flag up here. So what we can do is we actually check if that debug is set with the if debug flag. And then we can do end if. So code that we put inside here will only be running if that debug is true. So to send values forward to the computer, we're going to use the shuffleboard, smart dashboard. So what's happening here is we're telling the smart dashboard that we want to put a number on the smart dashboard. The key for the smart dashboard is yaw. So when we open that up, you'll see a block that'll say yaw. And then in that yaw, it'll have a value. And that value, we want to set it to get yaw. So get yaw, remember we created down here. And get yaw will get the navx yaw angle and it will return it back and show that data to you on your computer. I'm going to add in the rest of the sensor data that we want to see. So we have each encoder along with each RPM of the motor in case that's something we wanted to look at. So if you see now that this text is nice, you can actually see it. This means that it's live and it will work. But if we go to debug and we set this true to a false, you'll see now that this has gone dark. And what that means is this is now suppressed. So when you compile and run, this code won't run. So it won't be seen at all, which is a good thing to do because then you don't have to go in and comment out each line. You can just set one little debug flag at the beginning and that sets everything. However, we do want it to run so we can actually show you the sensors working. So I'm going to change this back to true. Oops. And you'll see this go back to highlighted normal text. And that's it for training.
You know, do we just want to maybe go back to the top and go down slowly, just in case somebody's trying to type all this in real time as you're going? So we'll just review what's in the training.h file or the training.cpp file. Okay.
Yeah, so we have our include statement, which includes our header. We created a debug flag for turning some debug statements off that we don't need all the time. We have our constructor where we will reset the encoders and reset the yaw. Then we have our motor flags where we set the appropriate flags based on testing data. For you, this may be different. It's always dependent. It's always robot dependent. Also depending on what you define as the front of your robot, for example. We have our periodic loop that runs every robot loop. And in here, we want to send all our sensor data to the smart dashboard so we can view it on our computer. We have our reset encoders, reset the yaw. We have our holonomic drive, which converts our X, Y, Z Cartesian coordinates into a formula that will drive the robot in a holonomic way, so any direction. We can set the running and stopped LED. We can get the encoder distance. We put in a simple formula to average out all the encoder distances. And then we have get yaw and get angle. Pretty simple for now. So one thing that we may want to do is at the beginning is use a controller to drive our robot around so we can actually see our robot work. Because sometimes it's not good to just always try to autonomously program your robot. You should be able to operate the robot 100% using a remote control, which can show you that, hey, my robot's actually working. And then you know it's just the code issue for when you do things. So to do that, I'm going to create a controller code for it. So first thing, I always like to separate my controller code from the rest of the code. So on the include folder, I'm going to right click new folder. I'm going to name this folder gamepad. And inside gamepad, I'm going to create another folder called another file, sorry, called oi.h. And this stands for operator instructions. Now, operator instructions can be a big file, but we're only going to really cover what we need for it. Oops. So the OI is actually a extension of the subsystem base. However, we're not using it as a subsystem. It's more just to make sure that it runs correctly as we want it to. So just like before, you have a public and private section of your header. In the public section, we are going to just create some easy access variables, functions. Now there's only 3 functions that I need for this specific training. And that's if we look at the remote control on the joysticks, we're only going to be using 3 axes. So on the left joystick, we're going to be using the X and Y. And on the right joystick, we're just going to be using the X. So we only need to define an X on the right side, and then for the left, the X and Y. However, you can continue down here and get the rest of the buttons and other axes that you need for your robot if that's what you're doing. In the private section, I'm just going to map out everything. So we use a PS4 controller when we do our robots stuff, and I've just mapped it out here. What you have is a USB port. I've defined it as 0. So if you have more than one controller plugged into your computer, you could define them as different port numbers. So 0, 1, 2, 3, 4, 5, 6, many as you want. And then with that, you can have multiple functions of what goes on. So if I wanted to plug in a robot, so if I just wanted to drive the robot around, I could plug in another controller, and Derek sitting next to me could operate the elevator if he wanted to, because we can separate the code that way. So I wouldn't be able to access the elevator, but he could. And then this is just the button map of the controller. So we have the buttons that are mapped between 1 and 14. And then we also have the joysticks, because their joysticks have their own button map. In this case, I have 0 to 5. And we can go ahead and save it. Because we're done with it. Now we need to create the actual source code that will take this data and actually do something with it. So remember, we created a new folder here. So we also need to create the exact same folder in the source side. So I'm going to right click on CPP, new folder, gamepad. And inside gamepad, I'm going to create a new file, oi.cpp. And in oi.cpp, we are going to create the code that will return our data that we require. So first, we're of course gonna take in our gamepad OI header file. We're also going to add the joystick. And math.h. So the joystick is the actual interface library that will read the joystick data. And then, oh, I don't want to see. And then we're going to do some calculations as well. So let's create the joystick. So here we're creating the joystick and then assigning it to the USB port 0 that we defined back in our header file. Now we can just create our 3 functions that we need. So our right drive X, our left drive Y and X, and then we can return that value. I'll just create the little value here, a function, and then I'll explain it. Okay. So what's happening inside this function for our X drive is we are grabbing the value of the X drive, so our X axis on our controller, and this returns a value of between -1 and 1. Now, with joysticks, when you pull them back and then you release, they will snap back to their origin point. However, over time, there's drift or other things that happens with joysticks. So that snapback point is not always dead on 0, 0, which means that you could be a little bit off. So what we're doing here is we're creating a little bit of a dead zone. So what I'm saying is if the absolute value of the joystick, so between -0.05 and 0.05, I'm going to say just return 0. Then if it's out of that 5% dead zone, we will just return the actual value that's being measured. Now, of course, you can increase or decrease this value based on your own controller or your own measurements that you need. Now I have to recreate this for the other 2. And because I'm a lazy programmer, I'm just going to copy.
No, you're not a lazy programmer.
Paste. And I can just change this right here. So left, 1. Then I have to remember I have to change the constant in here so it's correct. And that's it for my operator instruction class. Now, if I had the buttons or other things, I could continue adding that to the file itself. However, for this training, we don't need it as we're just driving the robot around. So I can close operator instruction. Now we have the core of the robot done. We can move to actually making the robot do something, because robots are boring if they don't do anything right there.
Absolutely.
Just a glorified paperweight. And to do that, we use something called commands. So in commands, you can see we have two folders. So there's commands in the include and then commands in the source. So what we're going to do first is create the command that we can drive the robot around using our controller. And I'm going to call that one manual drive.h. So in commands, under the include folder, right click, new file, manual drive.h. I have to create the header for this. So
I think how easy it would be if you could just cut and paste all this code into the chat and they could cut and paste it into their system.
I gave it to everyone already.
I know.
So here's our include statements. So we're including the command base and then the command helper. And we're also including our training and so our subsystem that has our robot drive in it. And then our operator instructions, which has our controller in it. Now this says red. We'll just ignore it for now. It's not an issue. So class manual drive. Then we need to extend the command helper. So inside this class, we can now create the header for our thing. So public wise, there are five main things that need to be defined for this to work correctly. So we have our constructor here where we're going to pass in a pointer of our instance of our training and then a pointer of our instance of our operator instructor. We also have the built-in functions that we need to override in order for the command to work correctly. So we have initialize, which is called once when the command is called for the first time. And then we have execute, which is called every single time the command is called until the command is told to stop being called. We have end, which is called right before the command ends. And then we have is finish, which you use to tell the command to end. Now we have some private variables that we want to create. I'm just going to copy this in and then explain it. So we don't need the, wait. Okay. So what we have here is I like to ramp up my gamepad just to create a smoother output when the robot's driving around. So we have our three inputs are our Y and X on the left joystick and our X on the right joystick. And then we just have some delta calculations that we use for the ramp, a ramp up constant and a ramp down constant, along with a delta limit for that ramp math. And then we have our localized instances of training and OI that will be passed and assigned to for when we do the code inside our drive. Now, if you notice here, there's this red line at the top. This is an issue with VS Code. It's not an issue with your code. So to get around this, what you'll have to do is you actually exit. You have to make sure that you have no open windows and everything is saved. You can open up the command palette and you're going to look for a command called C++ refresh C++ IntelliSense. So you could just search refresh C++ IntelliSense. What this will do is it'll rebuild the background source grabbing data so that it'll work correctly. It's a weird bug in VS Code that they have not been able to solve yet for some reason. And you'll see now that when we go back to manual drive, there's no more red lines because everything's working. This, however, is red because we have not created the class of manual drive yet. So it's tossing an error. However, once we create the source of it, everything will be good to go. So we'll do that right now. So in commands, I'm gonna under CPP, new file, manual drive.cpp. In here, we're going to, of course, include our header file.
Once you finish this one, we should probably take a break for everybody and let them have a little rest.
We need the constructor. So here is our base for the manual drive. And in here, we have our constructor, our initialize, our execute, our end, and our is finished. Because if you remember in the command helper here, well, in this header file, that we had to create these 4 functions that are overridden. And these are the 4 functions here that we had to add. And you'll see why we have. We're not actually using the initialize because we're not doing anything when we're driving around. But when we do some autonomous routines, we may want to initialize something. In the constructor, I'm taking the instances, so the pointer instances of our training subsystem and our operator instructor, and I'm assigning it to what's required. So our localized one, so train equals training, and then because they have the same name here, I'm going to use this OI. So my OI defined here is assigned to what the value of this is. So now we have to add some code into execute and end for everything to work. So because we're not using the Y, I'm going to get rid of that on the right side. So I'm doing first inside execute, because remember this gets called every robot loop. So it's going to go top down. I'm going to grab my joystick data from my OI. So my Y, X, and 2 X's, and apply it. And then I'm going to just create the simple ramp math where it'll grab a delta and then calculate if that delta is past the limit and then do the ramp function. Then at the end, with all my ramps calculated, I'm then going to assign my values from my joystick to my holonomic drive. As you can see here, train, holonomic drive, my X, Y, Z, where X is coming from my left joystick, X value. Y is coming from my left joystick, Y value. And then my Z is actually my right joystick, X value. Now, if you notice, the Y axis value is inverted. So I put a minus in front of it. And the reason for this is joysticks are inverted. So when you push forward, you actually get a negative value. When you pull back, you get a positive value. And this comes from flight simulators. And when controllers were first made, that's how it's done. That's why, you know, when you pull up, you go up, and you push down, you go downwards.
Good to know.
Yeah. Microsoft.
Yes, I believe, except that the Logitech F310 is backwards.
Maybe.
Yeah.
And then when our command ends, we want to make sure that just in case we set our values to 0 for our holonomic drive, so that if the command ever ends and we can't control it anymore, we want to make sure it doesn't move. So it'll call this and stop the motors. And that's simply it for the manual drive source. Now, if you notice, we go back, there's still an error here, and that's because we haven't actually created the instance of this class yet, so it doesn't know what to do. And to do that, we have to go to the robot container and add it in. So in robot container, so we're going to start with the header. We have to add these in. Let's first add some imports that we need. I'm going to add more imports that are here currently because we're going to be adding stuff later on. I'm just going to cut. Oh, I can't. All right. So I just added in some header files that were used later, along with our manual drive command, our two subsystems that we created. I will leave these other ones for now, and we will get back to it later. So let's add this. And then in private, we're going to create OI. Now, if you notice, normally this subsystem will be defined in private, but I moved it to public for a specific reason that I will show you later. Oh, there's a chat.
This code was sent out on.
The code is already available on our GitHub in the example projects folder. So we're going to, all right. This is it right now, and we'll come back later to add more to this when we start creating some of the autonomous routines. So in our robot container CPP, we now need to add some more code. So in the actual constructor, we're going to say training dot set default command manual drive, and then we're going to send our two instances to it. Oops, there we go. And that's all we need to do for now. So what we've done here is we've told the subsystem, which is training, that its default command is the manual drive, and then we're passing our instances that we created in the header file, so here and here, to that manual drive command. And now also, if we go to the manual drive header, you'll see there is no longer an arrow line under command helper. Yeah. So under command helper, there's no longer an error because everything has been defined correctly. So it's good to go. Now, if we were to run our code now, we'd be able to drive our robot with no issues. It would work. However, we're going to add some more stuff in there so we can show everything at once. But Derek said it's probably good that we take a break. So we'll take a 10-minute break and we'll come back at 8:30 our time.
Yep, 8:30 will be good.
We don't know what time that is for you guys. So 10-minute break, and we'll be back at the 30-minute mark.
Yeah, unless you're in Newfoundland, in which case it would be the full hour mark. But
Yeah.
10 minutes from now, we'll come back.
Yeah.
And I've just posted some stuff in the chat. We created a link for your resources. Okay, so day one's briefing is there as well. Next week, we'll post the 2 sessions, the videos that have been recorded. We'll just edit them and compress them for you. And then I'm about to send the link for the GitHub for you where all the example code is as well. Okay. And James is going to go there anyways.
Easier post exactly.
I wanted them to see it all. All right. Either way.
All right, we're back. So we've created the controller now, but now we want to add some really cool autonomous commands, do some stuff.
Stuff is good.
So the way I like to do this is to break up into different folders and things and everything that goes on. So in commands, I'm going to create a new folder called robot commands. So in this folder, let's start with a simple rotational command that you'll use on the cleaning pad, for example. So in here, I'm going to go rotate 720 because we want to, well, the TP says that you have to rotate 540 degrees, but we're going to do 720 degrees because it's easier to show a robot spinning twice. So let's go with that. It's going to add some include statements here. So this is starkly similar to what we've done before with the other command that we made for the manual drive, because we're just making a command. We're not actually doing any autonomous in here. It's just the command itself. We have to create another file that runs this command to schedule it correctly as an autonomous command. So what we're going to do is same thing as before, just create a rotate. And inside this class, we're going to add some functions and variables that we want to keep. So as we can see, we've added the PID controller because we want to, turn this robot exactly 720 degrees. And the best way to do that is using a PID controller. And also by using a PID controller, when we've turned that exact 720 degrees that we want to do, we can stop the command, which will allow us to go to another command. So if you remember with the command-based system, if you don't stop the command, it will never end and you'll never be able to go to another command and continue your robot. So here we are only using our training subsystem so we can pass the pointer instance through. Then we have our normal 4 functions that are required. We have our local training. And then we also have our variables that we use for the PID. In this case, I'm just using a simple P controller. I've not calibrated it. It's good enough for what we need to do for the training. However, you can update this for what you needed to so you can be right on the money that you're requiring. And then I've also created the PID controller that we're going to use. And I simply named it PID. So it's very obvious as what it is. So we're going to save that. And you can see the source files are red again because, that IntelliSense bug that's in VS Code. Now in commands, we have to create the same folder that we created here. So a new folder, robot commands. And we're going to create the file rotate 720.cpp. Now, of course, as always, you need to include your header file that you made. Now I'm just going to copy in and then explain everything instead of typing it in manually. So here we created our constructor. We're only using the training subsystem, so there's no other parameters to put in. And we can assign that subsystem right away in the header, so you don't have to do it like we did before. And then we also have to add the requirement that we're using this subsystem. This just links everything together so it works correctly in C++. In Java, there's a bit different ways of doing it, but for C++, you have to do it this way. Then we have our initialize function. As you recall, in the other command that we made, the manual drive, we did not have any initialized code running because we didn't need to initialize anything. Whereas this time, we want to actually initialize some stuff, such as setting the tolerance of the PID and also zeroing the yaw to start at 0. Because if your yaw is something else and you want to go to a different degree, you could get unknown, like your robot could do something unknown that you don't know. So you always want to control what needs to be done. So in this case, with PID set tolerance 1.0, I'm saying that I want my degree value to be within 1 degree of accuracy. So that would be 719 degrees to 721 degrees. Because for me, that's good enough, right there.
Yes.
Of course, you can tune that further if you wanted to, but that's up to you. For me, 1 degree is on the money. Then in our execute, this is where the holonomic drive and the actual PID comes into place. So we're going to set our drive, holonomic X, Y, Z. Now, if we remember, X and Y is our forwards and sideways translation, where the Z is our rotational translation. So we can set our X and Y to 0 because we don't want to drive forward or sideways. We always want to translate in the Z direction. So we're only going to use the Z parameter here. Now, we have to clamp the output of the PID to make sure that it stays within a variable range that we want. Because the PID could go outside of that -1 to 1 range that we want, or we might be able to constrain it to a different speed. So we want to drive slower or faster. So in this case, we're clamping the output of the PID to -5 or 0.5. So what I'm saying by that is I want the robot to go at 50% speed either way, depending on what my PID output calculation is. And in this case, my PID output is I'm calculating the angle that I'm getting from the NavX, and my set point is 720 degrees. So each time this loop runs, we're getting the current angle and comparing it to the set point. And then it will then output what the PID is outputting. So what the actual calculation calculates. Now, the reason we use get angle instead of get yaw is the yaw value will only return a value between -180 and +180, because that's a yaw value to give you a normal direction. However, because we're going past that distance, we want to use a continuous angle. So to do that, that's what get angle is. It's a continuous angle. So if you were to keep rotating your robot around in one direction, it would just keep adding that angle up and up and up and up. And it saves it. You can keep going and going and then go back the other way to get back to 0. So in this case, we're going to use the get angle and we're going to put 720, and it will turn that 720 degrees. If I was to put get yaw and then put 720, it would never reach this value. So it would just spin forever. And that's the execute. Now in the end, as before, if our command ends, we want to stop the motors. So we're going to call our holonomic drive and we're going to set 0 to all XYZ because that will stop the motors. And then if you remember, if we want to end our command, there's this is finished class, and we want to return a value. In our previous one, we were returning false as we never want the command to end when we're driving the robot around. So we return false. But here we do want our command to end. So we're going to check, is the PID at set point? So has the PID hit that 720 degrees that we want it to be at, or within that tolerance, so the 719 to 721. If it's in that range, this returns true, which will then activate this function. So the scheduler will check, hey, this command is done, and it will end this command, calling this motor stop, and it'll move on to the next command that you have, or it'll just stop. So that's it for rotate 720. Now the thing is, this is useless code unless we actually add it to an autonomous routine. And to do that, we have to create another file. So in this case, I'm going to be obvious here. So in commands, I'm going to create a new file, and I'm going to call it
rotate.720?
no, cleaning pad.
Cleaning pad. Ah, because that's where the rotate is going to occur. Got it.
Yes. So in cleaning pad, we're going to first add some include statements. So in this case, notice how we have our command helper and our command base that we have in our other command here. But we've also added another one called sequential command group. This sequential command group will instead actually tell your commands what to do, as it creates a sequential commands as like a list. So you can call one command after another and just keep going. There's also a parallel command group if you wanted to run commands at the exact same time. Cleaning pad. Spelling. And that's simply it for this autonomous header file. It's normally just a constructor. There's nothing else that you put in. And then we're going to create the same thing, but the source file for it. So in the command of the source, we're going to create cleaningpad.cpp. We're going to include our header file. Oops. It's going to include some other files. We actually have to include our rotate 720 header because that's what we actually want to use. Now we include the parallel command group in the source file, not the header file. If we include in the header file, there's some weird error that comes up. So we have to put it in the source file for some reason. cleaning pad. Cleaning pad. Oops. All right. So there'll be an error here until we add everything in correctly in other folders. So what's going on here is we're including our two header files that we're using. So our cleaning pad header and our rotate command header. Then we also include the parallel command group because we need the timeout, and the timeout is only part of the parallel command group. It's not part of the sequential command group. So in our constructor, we're grabbing our training instance pointer, and then we're going to just pass it on to the rotate command. So here we're calling the rotate command, and we're adding it as a command to the sequential command group. So what's going to happen here is it's going to rotate 720 degrees, and then afterwards just stop. Now, because if we remember, this command has to stop in order to go to another command. So even though we added a return statement here that will check, there are instances that an error may occur and we never actually reach the set point and is finished as not called. So what we want to do is add a timeout. So if we measure that our robot should be able to do that turn in say 10 seconds, we're going to add a timeout for 15 seconds so that if it never ends, we can still stop the robot and continue on with what we're doing. Because there's nothing worse than your robot just stops and does nothing and you have no idea what's going on. So in this case, we're adding this timeout to ensure that if we had another command, so for example, I wanted to add another rotate 720 drive, that it would actually get to this point. Because if I didn't have the timeout, we would never make it to this point. So that this one would never get called. You'd always be stuck in this. So that's why we want to add this timeout. So now that we've done the source for this, we have to add it to our robot container so that we can actually tell it to actually run that command and not something else. Right? So what we're going to do is include, we can get rid of this example command and example subsystem now because we actually have something to send. And we're going to go include commands cleaning pad. And we notice there's an error here, so we're going to delete that because we don't have those anymore. And what we're going to do is I'm going to add a thing here called commands. So cleaning pad. Not those brackets. Always put the wrong brackets back. So. So essentially, I just want to add this instance to. Did I spell that wrong? I did. There we go. My spelling is always off a bit, so I always have to check. Then we don't need the configure buttons anymore. And we also want to add our auto chooser so we can choose what autonomous program we want to run. chooser. Person to command choose. Yeah, and that's what we added up here. So now in our robot container.cpp, we have to make some more changes as well. So I'm going to get rid of this pass through. No one wants that. We don't have configure bindings anymore because we don't need it. So now I want to add commands to the chooser, which is simple. It's just chooser dot add option. In this case, I want to add rotate 720. This is the text that you'll see in the auto chooser. So it's like a drop down menu. And then I want to pass into it what we defined here. Now, what is going on? Yeah, we don't want to return this. We want to return chooser get select.
Bracket out.
Maybe. I don't know. We'll figure it out.
You're missing a bracket somewhere.
Oops. Get tab. So here we're adding the chooser to the one. Did I spell it wrong?
Spelling counts.
I don't think so. Could be here that I spelled it wrong.
I see something on there.
Where?
Just saw it.
No.
No.
Probably spelled something wrong somewhere.
It was an OI.
No. I always spell things wrong. Oh, I put sequential command base. It's got to be sequential command group. There we go. Sequential command group. There you go. Now it's there. See, always spelling something wrong or doing some error. So now that this option has been added, everything's good to do. Now what's going on? Oh, just IntelliSense error, I think. So what did I do wrong there? Depot parallel command group. This has got to be race group there. See again, always put in the wrong stuff. Yes, it's the timeout is part of the parallel race group, not the command group. All right. So Derek wants to just turn on the robot there. My hand the power button. We can turn on the robot. It's got the fan in it.
Super fan. At least you'll know it's running.
Yeah. So now we're gonna run a build just to make sure everything's working. So run the build.
Blue, green, red, blue, green, red, blue, green, red.
As you can see, I built successfully, so that's good to know. I'm gonna check. So here we can see our robot. So world skills dash 1, 2, 3, 4. Click on it, connect. Now, if it's your first time connecting, it might ask you for a password, and it's password. You made it really simple. Okay, I'm now connected. Now I'm going to start control station console. When I open it up, it asks me for an IP address. So I'm going to go 10.1.2.3.4.2. Now I forgot to deploy to the robot, so I'm not going to hit enter yet. Let's go here. Deploy. So if I hit enter there and I didn't deploy yet, I'd have to restart the control station console before it would work again. I'm going to open it up. I can hit enter now. Oh, there we go. See, it'll auto open the shuffleboard for me as well. I'm just gonna remove these because we don't need them. So if you notice, all those encoder values and things that we made have all been added for us here. Automatically. So if we go back to our code, oops, in our training.subsystem, oops, all this periodic code that we added to send through to our shuffleboard is now here. We can see the data. So we can see our angle, our yaw, and then our encoder values. If Derek was to pick up the robot right now and then rotate it, you could see our angle and yaw will change based on what he's rotating it to. Now, if we want to, like we said, drive the robot around manually, in the control station console, we want to make sure we are in teleoperated mode. And that's by, if we're not in that mode, you can hit O and it moves to that mode. Now my controller is plugged into my computer by the X marked here. I can see that I'm connected. So now if I hit E for enable, you can see that I can drive the robot around with no issue. And I'm going to D to disable. Now, because we actually want to test the autonomous that we just made, if you remember in our code here in the container, we set our chooser to be in a tab called autonomous options. So if we go to that tab, whoops, you can see autonomous options here. You see there's a widget here called sendable chooser with a drop-down menu. By default, it's blank. Oh, my screen is paused for some reason. Oh, I'm only sharing that, not the, hold on, let me reshare the screen here. Sorry about that, we were showing the wrong screen. So yeah, all our data here auto popped up for us on the, as we showed in the cleaning. So our code that we set here in the training.cpp, so our debug smart dashboard code, has been sent correctly to our shuffleboard that we can see. Now, if we rotated the robot, you can see the angle and yaw would rotate as we want. But we want to set the autonomous. So in autonomous options, we have our sendable chooser. And that's what we created in our robot container. We added it to the chooser in a tab called autonomous options. So in here, we're gonna drop down, rotate 720. The check mark here shows that we are good to go. And it successfully chosen that option. So if we notice now, we're still in teleoperated mode. We want to switch to autonomous mode. So in our set control mode, we want to go to A. So we hit A on our keyboard, and we now switch to autonomous disabled. Now with in autonomous mode and our mode chosen, if we hit E to enable, we can see that the robot spun 720 degrees. If we go here, we can see it's a little bit off because it went a little bit past because the PID is off a bit. So now if I stop screen sharing, now you can view it in full screen. So if I was to run the command again, enable, we'll see the robot turn 2 times. And there you go. You can see that our angle is 724. So it's off a bit because the PID is not calibrated the best. Because as you can see, I just put in a peak calculation. Now, if you notice, see how the angle is 723, but the yaw is 3 degrees. That's because you want to use angle for this and not the yaw. You also see we got the encoder data here. And the RPM is 0 because it's currently not moving. If I were to run it again, I disable first. You can see that our RPM is running at about 50 RPM, which is what we want because the motors are 100 RPM, and we set our rotational speed to 50%. Back in the code, in our rotate 720p, we set our speeds here to 0.5 and minus 0.5. And as we saw there, it was rotating at 50% speed. So it was working as intended that we wanted. However, we're not really showing that the robot is running or not running, which is a key form of what is required in mobile robotics. So to do that, what we're going to do is we're going to actually flash the running LED or the stopped LED on the robot to show if the code is running or if it's stopped. Now, we already created that in our training code. We added the functions in there to set and stop the LED. So we can do all that in our robot.h folder of header, sorry. What we're gonna do is we're gonna add a simple thing here called void running LED. So I'll just create a extra function that we can add to our robot class. So also in our robot init, I want to add some code here. So what I want to do here is essentially turn the LEDs off at the start when the robot is first run. I'm going to add a simple global variable in here and count and move. Count equals 1. Previous equals true. So this will just help us when we need to switch between an on and off state. It's just a simple state management. So we wouldn't be able to do this if in our robot container header, if this training was in the private, we wouldn't be able to access it from here. So that's why it was moved to public and not private like everything else is. So at the bottom here, I'm going to add that running LED function that we just made. And all this function is going to do is make the running LED flash at a certain interval. Oops. Did I do that right? No. So back to the one. Oh, here. So what we're doing here is we're gonna have a simple counter that runs every loop, and then we're gonna check if the modulus of that count with 25, the remainder is 0, then switch between false or running. So flip it. So we do know that every loop is 20 milliseconds. So 20 milliseconds times 25, and you get a big, large number, right? Which is used as our off time or on time delay that we wanted. So you could adjust this if you wanted that LED to flash faster or slower. And in each loop, really, so in each periodic loop, that's what we wanted to add it into. Running LED. And then in teleop in it, we also want to add a simple M container dot training. We want to turn the stopped LED off because you don't want the stopped LED to be on when you're actually running. So it should be off. So this init makes sure that it's off. And then in the periodic loop that's called once every loop, it will flash the LED. Now we can do the same thing in our autonomous loop. Because what will happen is, even though our autonomous sequence is running somewhere else, the autonomous periodic is still called at the end of every loop for when you're in autonomous mode. So by adding the running LED function here, it will still flash the LED in the background for us, and we don't have to worry about adding that code anywhere else. And then the one thing that we want to do is when the robot is disabled, so it's stopped, we can, we don't have to put this in periodic. It only needs to run once. So we'll put it in it. So we're going to set the stopped LED to true. So that means the stopped LED will turn on. And we're going to set the running LED to false. We'll turn it off. So now if I build and deploy this code, sometimes it takes a while to build. Now deploy the code. So I'm going to run the robot in teleop mode first. So if I stop sharing so you can see better, notice how the stopped LED is lit up because the robot is not enabled and it's not moving. you don't see the Titan is flashing green, red, blue. This shows that it's detected the CAN signal, but the robot is disabled. If I were to enable the robot now, you can notice that the running LED is now flashing, which is telling me that the robot is now running. I can also see that the Titan is flashing purple, which is showing that it's enabled as well. So now I have two ways of seeing that the robot is running and is live. So I don't really want to go near. If I were to touch the controller right now, the robot would move. And if I hit disable, you can see the running, this LED turns off and the stopped LED is on. However, hey, we want to check, does this work in autonomous too? So let's switch to autonomous mode.
Which control function do you use?
A.
Control
A.
A,
No, just A.
just A.
So now we make sure that our rotate 720 is chosen. And then I'm going to hit. And then I'm going to hit enable on the robot to enable the autonomous mode. Now you can see when the robot comes around that the green LED is flashing, which is what we wanted. Now you can see the green LED is still flashing because our autonomous is still running, because there's nothing stopped at the autonomous. So the command is ended, but the autonomous mode is still running. So the only way to stop that is by hitting disable on the robot. On the control station, you can see it's now disabled. So some things to take into account. So that's simply one of the key features of world skills that was simply done by just adding a little extra code to the main robot section. That seemed very simple right there.
Sure, it seems simple.
So another thing we might want to do with the robot is drive it forward a set distance. Now, we already have most of this built in. We just need to tell the robot to do that. So what we can do is, we're trying to find Zoom here. Is we're going to add that to our code base here that we've made. So the first thing to do is in our robot commands, we're going to add another command, new file. I'm just going to name this one drive with PID H. I'm going to copy in a PID just to show you. And this is the drive with PID. So we have all the same imports that we've had in the previous ones. So if we were to look at the cleaning pad, you can see, oh, that's the wrong one. We want the rotate center. We know the imports here are the exact same imports as here. Now, here we can see it's got a different constructor with lots of inputs. And the main inputs here are our subsystem. And then we've created set points for our X, Y, Z, and then an epsilon for X, Y, Z. So this is the tolerance that you want to set it for. And then we have our typical 4 value functions that are required. We have our localized instance, our localized variables, our localized K values, and then we have our PID controllers that we define here. Now I just have to run IntelliSense again because we've added more stuff and it's that weird glitch in VS Code. Hey, it's gone. Like magic there. Like magic. And of course, we have that command helper error because we're missing things that are required for it to work. So now in our CPP robot commands, we're going to add the exact same file. So drive with PID.cpp. Again, I'll just copy it in because we're short on time. So in this instance, what's happening is I've included the header file. We have the constructor with all our inputs. You can see it just goes on for a while. Then we add our requirement of the subsystem training. In our initialize, we're going to set our tolerances just as we did with the rotate. We set our tolerance and we reset the encoders. Then in the execute command, I want to drive straight. So I'm going to drive the robot in the Y direction. So in this case, I'm going to leave my X direction as 0. So my X is 0. In my Y, I'm going to add a clamp with the PID calculator. That should be Z. Where I'm going to drive, get my average encoder Y, because remember we did that calculation where we meshed everything together. I'm going to use my set point Y, and I want to drive at 50% speed in the forward direction. And then for my Z, I want to keep at an angle that I set it to. So if, for example, 0, because I want to drive straight, I'm going to get my yaw value, compare it with my set point for Z. And I also want that to be a 50% tolerance on how it controls. If you wanted your angle to be more aggressive, then you can change this to 1 or -1. Just the same as if you wanted to drive faster forward, you can make this 1 and 1. For example, if you wanted your drive to be more stronger, for example, I could make this 75. 75. And if I wanted my yaw to not be as affected on the drive, I could make this like 0.1. But I don't want that. I want my yaw to actually stay straight. So I'll leave it as a half. And then, of course, if it ends, set all the values to 0. Now, when my is finished here, I don't want to use my Z value because my Z value would normally always be at the set point because you want it to stay at 0. So it's going to stay in that set point range and wobble back and forth. So what you want to use is your Y distance because that's where you actually want to go. Like I want to drive 2000 millimeters that way. So that's what I want my command to end. So I'll use my Y. So now let's add the actual command that's going to operate this command. The same thing as we had to do with the rotate 720. So in this case, I'm going to add a command in the command folder called drive length of court. Now, normally the court is 4,000 millimeters. Yeah, 4 meters. However, we don't really have that much space here, so I'm going to just do 2,000 millimeters.
Yeah, let's not go too far. We've got a short area here.
That's a bit far. So we see, just as before, we have our inputs, drive length of court, sequential command group, with only a constructor requiring the subsystem. Now I create the same command in the command folder, but this time the source for it. So drive with drive length of court.cpp. and just copy it and show it. So we're going to import the header file that we made. We're also going to import our command header that we made of the actual PID driving forward. We have our class here, then we have our command. In the command, you can see we're passing our training subsystem in. Our X value is 0 because we don't want to translate along the X axis. I set my Y set point to 2000 millimeters because we want to drive 2000 millimeters. My angle that I want to be at is 0 degrees, i.e. I want it to drive straight. And then my epsilon for my X axis is 0 because it's not going anywhere in the X direction. I set my epsilon, so my tolerance for my Y axis drive to 10 millimeters because I think being within 10 millimeters is fine for that long of a distance. Because when I get to the other end of the court, I can use my sensors to re-square myself instead of always operating off encoder data, which is probably the best thing to do, is always try and re-square yourself when you can. And then I'm going to set my Z epsilon to 1 degree as we've shown before. And I'm going to give it a timeout of 15 seconds. So now with all that added, we need to actually be able to tell the robot, hey, let's run this command. Let's not run another command. So we'll do the same thing that we did with the cleaning pad, where we have to add it to our robot container. Drive length of court. Drive length of court and create the instance of that by passing it through. And then in robot container CPP, we're going to add an option to our auto chooser. And that's simply all we have to do. We have now added that command to our auto chooser. We can choose it, run it, and see what happens. Hopefully it doesn't go backwards. Right there.
I'm ready.
You want to move it just over there so we can drive it forward
Which way?
with a lighter.
And then I'll turn it that way.
Yeah, but I don't know how much 2000 millimeters.
I'll go over there and be ready to catch it. You want to move it back a bit or just go?
No.
Oh, turn the camera. All right.
You just aim that camera. James wipes out. I'll edit that out. Still building. So now that we built, I'm going to deploy it. We're now deployed. We can also see that in my sendable chooser now, I have another option called drive length of court. I'm going to choose it. It's chosen it. Good to go. Very nice. You see my encoders should be 0. My autonomous is disabled. I'm going to stop screen sharing so that we can actually see the robot drive forward. And hopefully it works first time. And clearly it didn't.
Motor power.
Well, from what it looks here is that the right side was driving much stronger than the left side.
I would agree.
Derek, do you want to reset the robot? So I'm going to go in and just edit the values. And, all right. So let's build. I can just deploy. I don't have to rebuild. So I just changed the values so it's not as strong there.
Redeploying.
Yeah. Let's hit enable again and see what happens.
But
Now, if I share my screen, we can see that, trying to find Zoom, disappeared. You can see here that our data here shows the front left encoder was a bit short, but and the back left was a bit long, but the right side was good. So if it meshed all together and you did some math, you'd find you'd be around that 2000 millimeters that we were trying to get to, and within that epsilon of 10. Now, Derek reset it back to the spot just so that we can show, can we repeat that? So if I hit enable again, you can see it drove again. And our values are still the same or similar. So we could calibrate that, redo the PID so that's more tolerant to what we want. If we were to put it on the pad here, we can show again that just by changing this value here, and me enabling the robot, it'll rotate that 720 degrees. And there we go. So now let's do something a little bit more advanced. So if Derek could put it back over there.
oh,
Where is it? So what we're going to do now, just to show how you can add two different commands together, right? We're going to drive that 2000 millimeters, and then we're going to have the robot rotate, set that 720 degrees. So right now, the command is only just drive forward. So I'm going to add a comma, and I'm going to, because I'm a lazy programmer, I'm just going to go to cleaning pad, copy this, put it in there, it's saved. But you notice there's an error because I have not included that. And now the error's gone away. Easy peasy. So now I'm going to deploy the robot code. It's now deployed. I'm going to make sure that I'm on drive length of court, which I am now. If I stop sharing so that you can see it nice on the big screen, and I hit enable, we'll see it drive forward. And then hopefully at the end of that driving forward, it will rotate 720 degrees, which it's doing right now. Yeah. So hopefully that was an easy way to show you that once you have those commands made, that's the beautiful thing about the command system, is that I can just reuse it for what I need. So in this case, there's drive forward and then rotate, and I could just keep using it wherever I need it. So for example, you're doing path planning, you can do from point A to point B, and you can just keep calling that whenever it's required. Or to pick up a cube, place a cube. It's all just simple commands. And once you have it, it's just putting it together. And that's why we developed, for example, the core tasks, because each of those core tasks could be a command that you just continuously run based on what's required. So that's all for the training today. Hopefully you did learn something. We managed to do it in C++. We showed a lot of command structure, driving the robot around with a controller. And hopefully that's enough to get you going for what's required. If there's any questions, we can answer it now for anyone that has any questions.
Somebody had a question, where can I see the electrical connections?
We showed that in yesterday's stream.
Yeah, so those electrical connections were put together in yesterday's training. Fernando, I'm not sure if you were there, but that recording will be posted for next week. Just trying to figure out how to get to Boolean. This is the Frankel bow right here.
All right, if there are no questions, we're going to end it in 5 minutes.
Yeah, so we'll stay up, and what we'll do is we're going to compile these videos. We'll compress them, and they'll be posted on that same link that I gave you earlier that had the PDF of the day one presentation. Okay, so they will be posted there. And just for that junior question from yesterday, I have taken note of that. It is currently scheduled for the same 2 days. So we'll discuss if it's an issue for you for the court. In fact, if it is an issue, just send me an email on that, okay? And I put my email in the chat, and then we can talk to World Skills Asia and come up with a plan for that, okay? That's actually expensive.